Yeah, okay. So as Dimitri mentioned, this is a practice talk for my dissertation defense, and most of the slides are already like close to finalized. They could be improved cosmetically. And I think I'm missing one research subject still, so it's not fully complete, but it should be enough for a good test run today. And if you saw the slide number, it looks kind of daunting, but there's a lot of transition slides, and a lot of them I shouldn't spend more than a minute on. So it should fit. I guess what is a typical dissertation time length? Like 45, 50 minutes for the defense?
Did you have a person who recently experienced it, Levi? So he probably has the active memories. But
okay,
yeah, 45 should be fine.
Yeah, that's the target length anyway. And yeah, okay, yeah, I guess I'll start. So my name's Aaron Forde. I'm a PhD defense candidate defending my thesis at North Dakota State University. I'm a student, a part of the Materials Science and Nanotechnology department. And today, this presentation of my defense will be about the photophysical properties that occur in lead-halide perovskite nanocrystals. And before we get to the material of focus, we'll give some background behind the material science, like I guess paradigm, and why nanotechnology is important for future applications such as optoelectronic devices, which will be the most relevant technology application for the research that I've been doing. So material science as a whole, it's not really a discipline by itself, it's interdisciplinary, and it's more of a kind of a mindset. It can be kind of visualized as this interrelation between these processes. So you have the corners, which make up structure, properties, performance, and processing. And the way I view this kind of a triangle or this pyramid is you have structure property relationships for materials which are affected by their processing, so like heating, cooling, and so on. And then how the processing and structure property relationships impact performance. And at the center of all this is characterization, so how you do the measurements on the material. And in this case, I'm a computational material scientist or chemist by training, so a lot of the characterization is using numerical simulations in computers. And also another aspect of material science is that it's a fairly broad subject, so you have to be able to understand the material's properties all the way down from atoms, so this nanometer scale on the length, and how those properties can potentially impact all the way up to meters. Maybe not directly impact, but if you're trying to build a device, you have to be able to understand many of the length scales involved. So that's about 10 orders of magnitude of length scales you have to consider. But then there are also kinetic processes, which can happen on 15 orders of magnitude from femtosecond to seconds. So it's a fairly wide spectrum that you have to consider for modeling materials. And in this case, I will be spending most of my time looking in the bottom left coordinate, so femtoseconds and nanometers. And so a lot of that is abstract when trying to explain it to, I don't know, relatives and such. So probably the most successful example of material science like thought process is the Manhattan Project during World War II. So it all essentially starts from, I guess, Einstein's physics of M equals mc squared, and that there's an enormous amount of energy that's stored within atoms. So the structure property relationship between atomic structure and then their nuclear processes. So that was generally known for a while, but then it took chemists such as Glenn Seaborg to be able to process uranium and uranium isotopes into purified forms of plutonium. And in this case, what's shown in the vial is plutonium hydroxide, which is about micrograms, which can then be reduced into pure plutonium metal. So getting gram scale quantities of these nuclear materials and then incorporating them into devices, which in this case were designed to make big booms, which they were able to successfully do. So within a fairly short time span of less than 10 years, we were able to understand atomic and subatomic processes and then use them into, incorporate them into devices, which impact still. So nuclear bombs is one type of device, but the most relevant application I'll be talking about is optoelectronic devices. And probably the two most well-known devices are photovoltaics and LEDs, which are both, well, they're very similar in that they're both classified as photodiodes. So you can either shine light on the material to generate the photovoltage, to generate power, or you can electrically pump them, so send electrons into the material and get them to emit pure colors. And these are very important for technology aspects because we need sources of clean, sustainable energy, which we can get from photovoltaics. And then LEDs have shown to be much more efficient and ultimately cost-effective than incandescent bulbs, which require heating as opposed to electrical pumping. So in general, you can view photodiodes. They have generally, you can arrange their structures in a lot of ways, but they all have the same components. So on the left panel shows an energy diagram of the alignment of the energy levels that you need for photodiodes. And on the right shows like a device architecture, so how the materials would be layered. And in general, you need a photoactive material. So in the left panel, that's the orange column, and in the right, that's the orange or the red block. And so those are photoactive, so they absorb sunlight in the case of photovoltaic. And then to get them to run a current, you want the active material to donate its electron to an electron transport material and the hole to a hole transport material. And in those layers, they eventually transport the charges to our more conductive regions and then eventually power the circuit. And so in general, for material science research, you consider each of these materials individually, what would make a good active material or transport layer. But you also have to be able to consider like their interfaces, because you can potentially have losses there as well. And so in the case of photovoltaics, it's generally known that with certain assumptions, that there's a maximum amount of efficiency you can get in the device. So this figure on the right, so there's generally 4 regions. So there's the usable electric power, which is the black region. So that's the device energy you can harvest as a function of its band gap. And then there are 2 main losses. So you can, depending on the size of the band gap, you either lose energy because the material can't absorb the correct amount of photons, so this pink region. And if the photon energies are too high from the sun, you eventually lose all that energy as well to thermal relaxation, so this green figure. And Yes, so these are the general two assumptions. So energy of charge carriers lost, so the green region, and then for every there's also another assumption: for every photon absorbed, you only get one charge carrier. And so the reason that people look at nanotechnology is that they can overcome these couple of assumptions potentially to increase this black region of usable electric energy. So before describing nanotechnology, I'll just give a brief idea of what nanomaterials are. So in this case, I'll show the fullerenes, so just carbon-based materials. So graphite is a common material that's known. It's what we use for writing in our lead pencils. It's essentially just layers of 2D sheets of carbon. And you could think to yourself, well, it's possible just to isolate those layers by themselves. And that's known as graphene, which is a two-dimensional material. You can also consider that if you have the right size of graphene, you can roll it up into a tube, which are known as nanotubes, which would be classified as a 1D nanomaterial. You could also imagine that this 2D sheet could be wrapped into a ball, so a 0D material. And so those are how, I guess I should mention quickly that 2D, 1D, and 0D just are defined as like aspect ratios. So in the case of the graphene, it's like literally one atom thick, but you can have the other two dimensions as like micrometer scales. And so you can make nanomaterials of various chemistries and try to incorporate them into optoelectronic devices. And the main reasons that nanomaterials are popular for optoelectronics is that they have highly tunable electronic properties. So you can, based on the dimensionality, you can tune their energy levels as a function of their dimension. And it is also possible to try to control the kinetic properties of charge carriers. So one example is that nanomaterials carrier-carrier interactions are enhanced. And it's well known that one of the most popular recombination, not popular, but one of the most prevalent recombinations is Auger recombination, where if you have multiple excitons in your material, that instead of having two different recombinations of two excitons, that one of the excitons will non-radiative donate its energy to the other, which eventually turns into unuseful heat waste. But from a different perspective is that you could start from a fairly high single exciton state. So in this B panel, so if you have a excitation, say at least 2 times above the band gap of the material, that theoretically it is possible to non-radiatively generate 2 separate charges from that. And this is known as multiple MEG, and which has been observed in various quantum dots experimentally. And so this is interesting because it would break the second assumption I described earlier for the limit of photovoltaics. So that's just a practical example, but the focus of my dissertation will be more on these carrier lattice interactions shown on the right. So one of the main losses in photovoltaics is thermalization, and it's been predicted that nanomaterials, that you start to get very large subgaps between electronic states, which are out of resonance from thermal energies, that it should be able to theoretically slow down charge carriers, and you can extract that hot charge carrier to generate a higher photovoltage, which would break the other assumption that I described earlier. And like I mentioned, most of my dissertation will be focused on carrier lattice interactions. And briefly, I'll describe the material focus for this presentation. Lead-Halide perovskites. So they were initially discovered in 1958, and they're composed of three chemical species. So lead, which are these gray atoms, and they're coordinated octahedrally to halides, so these X positions. And with those by themselves, the stat lattice is fairly unstable. So these A plus cations fill the voids in between these octahedra. And I'll just briefly mention that you can have various polymorphs of the perovskite. So the figure on the left would be the 3D connectivity shown in panel D, but it's also with various chemistries to have disconnected regions of the lattice, which would change the connectivity. But for the bulk of this presentation will be on 3D perovskites. And I guess I'll just quickly mention that perovskites were like fairly well characterized up to 2009, but that's when the energy community started trying to incorporate them into photovoltaics. And there was an explosion in the literature because they showed very good properties for photovoltaics. Within 6 years, they were showing 18% conversion efficiencies, which is competitive to what you'd see commercially. But instead of but the specific lead-halide perovskite that I'll focus on my research is perovskite nanocrystals, which were first published in 2015. And you can see that they're very popular with over 4,000 citations of this work within 6 years. So these themselves have introduced a lot of excitement into the community. And the reason is that you can see in this left panel, those are the literal nanocrystals, so they're little cubes. And they are very bright and fluorescent, and you can change their emission wavelength across the visible spectrum simply just by changing the halide. So just changing the chemical substitution all the way from 700 to 400 nanometers. And you can fill in the in-between gaps by just mixing halides. And in terms of technology applications, they outcompete the standard televisions. So this is a chromatic graph where the dotted and solid white line represent the standards at the time this was published, and then the black dots show the color purity where these nanocrystals are respectively. So the main takeaway is that the blues are bluer, the greens are much greener, and the reds are redder. So you get very nice picture quality. If they were used as displays. So I guess the holes in the literature, these lead-halide perovskites when they were first published, is that one of the interesting ones for us computationally was the impact of spin-orbit coupling on the carrier dynamics, because the lead ions experience very strong spin-orbit coupling, and they compose much of the conduction band. And spin-orbit coupling usually isn't incorporated into a lot of dynamics simulations. So that was one of the main holes in the literature when first starting my research. Then these materials showed to have a very sensitive surface chemistry. So this vial on the right is a purified version of cesium lead bromide made in Dr. Hobby's lab. And when you try to process them with various solvents, you can see that polar solvents tended to make them dark or dissolve them, so that's why they don't have color. And even non-polar solvents have the potential to darken them. So they have a very peculiar surface chemistry in that the ligands aren't very tightly bound. So there's a lot of research in that area. And the last one I'll mention is that these materials showed to be very defect tolerant, which is unusual for semiconductors. It's like if silicon has like a fairly low density of defects, it renders them pretty useless. Whereas with perovskites, you can make them on a bench, and then they'll still emit fairly well. And some have postulated that Fullerenes could be the reason why that they show these large defect densities, because Fullerenes can theoretically be protected by the lattice from the defects. And there have been a lot of interesting experiments trying to isolate Fullerenes. And the one paper that caught my eye is that one group was able to do IR spectroscopy and observe increasing signals which they attribute to Fullerenes with increasing temperature. So going from blue to green in this figure on the bottom right. So cold temperature, not a lot of Fullerenes, but with increased temperature, you have increased absorption due to more Fullerene states. And so those are the kind of the three paths I follow for my research. And so, as I mentioned in the beginning, I am a computational chemist or material scientist. So to be able to describe electronic structure and dynamics in these systems, we need a fairly robust methodology, which I'll go through now. So just to be thorough, I guess for molecular and quantum dot systems, like electronic structure generally starts with Hartree-Fock, which composes molecular orbitals as Slater determinants, which automatically include exchange correlation, but Hartree-Fock by itself is rather inaccurate because it lacks any description of electron correlations, which require heavy-duty theory to get more accurate results. So, but as an alternative method, which will be the workhorse for the simulations done here, there's the development of density functional theory. So instead of considering the wave function, a clever physicist thought that the charge density of the molecule or the solid itself should determine the external potential. So if you start with the charge density, so this top equation of the occupied states, and say that the external potential, this VEF, is a functional of the density, you can write single particle equations similar to a wave function method to get cone-sham orbitals, so these phi IKSs, and then eigenenergies EI eigenvalues, so the energy of the orbitals. So the benefits of DFT is that it's been readily implemented in software and has a reasonable trade-off between the sizes of the systems you can look at and the computational cost. But in principle, there are a lot of approximations, so the cons of DFT, which are mostly you need to be able to compute transition dipoles, which determine the intensity of the optical transitions. And for this thesis, we operate in the independent orbital approximation, so we neglect bound Coulomb or exciton states, which requires a heavy-duty theory to do that, which would be costly for the size of the systems we look at. Right, but I'll mention that for strongly confined nanoparticles, like I'm going to, like I looked at for my research, the transition dipoles compare favorably well to higher order methods. So it's a reasonable approximation to make. And then the most important computed observable for this whole dissertation is the non-adiabatic couplings, which describe electron-phonon interactions. And so the goal of these non-adiabatic couplings is to describe the vibronic frequencies which mix together various electronic states. And to do that, within the DFT software, we implement on-the-fly couplings. So we do molecular dynamics, which propagate the ions according to Newton's law. So the acceleration, d squared dt squared Ri, is equal to the force acting on the ions divided by its mass. And then the force comes from the external potential from the Kohn-Sham equations. And then to keep everything thermalized, you set the velocity is equal to a thermostat to keep temperature, or so you can change temperature. And at each time step, you can compute these non-adiabatic couplings, which is shown on the very bottom of the screen. So Bij is the overlap of different orbitals due to the change in time and the trajectory. And so then to implement excited state dynamics, we take these non-adiabatic couplings and process them into state-to-state transition rates in red field dynamics. So I'll mention, just for a brief overview, to do dynamics, we need equations of motion. And one possible method is to use a Schrodinger equation approach, which is how methods such as surface hopping is implemented, where changes in the expansion coefficients of the wave functions are changed along the trajectory. But an alternative approach, which is equivalent, is to look at density matrices. And yeah, formally they're equivalent, but density matrix formalism is nice because it naturally includes occupations as a part of its formalism. So it's natural to describe changes in populations due to thermal motion. And just to give an idea of how the dynamics are run, which will be shown later in the slides, is that these non-adiabatic couplings are processed into red field tensors, which is visualized in this main figure, by considering correlation functions. So this Mij, and then we take Fourier transforms of the correlation functions to get the red field tensor, Riijj. And the way to read this tensor is that the x and y axes correspond to specific orbital states. And then the z-axis refers to intensity of the peaks. And you can consider that this tensor can be broken apart into 4 different sections. So you can have, so these blue regions corresponds to intraband in the conduction band, so RVV, and these yellow peaks corresponds to intrabands transitions in the conduction band, so this RCC, and then the reintroduce the interband transitions. And there are, first I'm going to look at surface chemistry. So just to give an idea of the model that is used as the workhorse for this dissertation and the surface chemistry of perovskite, so I'll just quickly go through how the model that we used was made. So the main material is cesium lead bromide, which has a unit cell shown in the middle. And then we replicate that a couple of times to generate this inorganic core, which is composed of lead, bromide, and cesium. But then nanomaterials, since they have surfaces, they're very unstable. So you need passivation ligands to separate or to keep the surfaces stable. And then, based on the experimental paper from the original synthesis, there are three possible pairs that you can place at the surface, where the minus anions will coordinate to lead, and the positive cations will coordinate to these A vacancy sites on the surface. And yeah, the main workhorse model is composed of these carboxylate anions and then ammonium cations, which sit on the surface. And so this would be like a 2 nanometer quantum dot overall. And a common way to just get a, I guess, fundamental or simple grasp on the photophysics of quantum dots are these particle in a box. I guess not theories, but just simple models to try to understand trends that occur in quantum dots. And so in the green panel, it's just an overview of typical particle in a box solutions that you'd find in a physical chem class. So you have infinite barrier potentials at each of the sides of the cube. And then the solutions will be standing waves, or these sine waves, on the interior of the box, where you can have different solutions based on these ny, nx, and nz quantum numbers, which are kind of range from 1 to infinity in principle. And then these quantum numbers also determine the energies or eigenvalues in the box. And so a way to consider the energy levels is this top right panel or figure, which are determined strictly from the particle in a box equation shown on the left. And so the left feature would be the conduction band, and then the red area corresponds to occupied states, and then the white region corresponds to unoccupied states. And then the insets within this figure show the particle in a box function. So you can see that these lowest two peaks, they are spherical in nature, which can be referred to as S-bands. And then the next three, the lowest energy states, have these nodal characteristics, which can be described as P-bands. And so this comes from just considering particle in a box, and the bottom shows a diffuted density of states, just from a simple spin restricted calculation. And I guess the main thing I wanted to show is that from the DFT outputs, if you look at the cone-sham orbitals, you can see that the lowest two energy states agree fairly well in terms of how the wave function should look. So there are nodes because of the atom sites within the quantum dot, but if you just consider the envelope function, you can see that for this SH band, it resembles fairly closely to something you'd expect for sine squared. And then you can see the same for the SE state, where there's a little asymmetry, but you can still see that at the boundaries, wave function decays, and in the middle is a maximum or near maximum for the charge density. then instead of showing these orbitals all the time in future figures, I'll just refer to them as SH and SE bands for notation. And I think I removed this slide for time. And so then, yeah, 37 minutes in, and then we can get to the meat of the presentation. So the attempt to describe 3 studies that I've done for my dissertation work, which looks into the holes in the literature that I described earlier in the introduction stage. So the first slides will be, so the main takeaway is that due to the large spin-orbit coupling from the lead atoms in the conduction band, and then strong confinement for our 2 nanometer nanocrystal, gives rise to slowed electron cooling. And I guess for this work, the methodology update is that we had to include spin-orbit coupling, we have to update the methodology we use, which requires using non-collinear DFT, which produces spinor orbitals, so these phi I SKSOs, which allow to incorporate the spin-orbit coupling energies into the simulations. And then I'll show that it's spin-orbit coupling is definitely needed for accurate description of the electronic properties. So this figure compares without spin-orbit computing density of states without spin-orbit coupling, so the panel on the left, compared to including spin-orbit coupling on the right. And the main takeaway is that the band gap shrinks by approximately 0.7 eV due to the strong spin-orbit coupling in the conduction band, which spreads out the energy states over a very wide range of energies. So it decreases the density of states near the conduction band edge. And then to do the dynamics, we implement molecular dynamics. And on the left, there would be a video which shows jiggling and fluctuations of the atoms from the trajectory, which I didn't include just because the file sizes get very large. And on the right just shows the changes in energy during the trajectory. And then at each time step, we compute these non-adiabatic couplings with spinor orbitals, which has 2 different contributions due to the way that they're constructed. Oops. Okay. And then from the dynamics, those non-adiabatic couplings are processed into Redfield tensors, which are shown on the right. And yeah, I don't have anything else interesting to say about them at the moment. But then these are used as the state-to-state rates for the dynamics. And then to choose initial conditions, we choose a bright photo excitation state. So we choose HOMO minus 9 and LUMO plus 10, which would be these states as visualized within the density of states. So they're like, I don't know, 0.3 deep into the valence band and then like 0.7 into the conduction band. Then to visualize the dynamics, I will use these green figures. So there's a lot of parts to them. So the color codes correspond to photo-induced charge density. So the green is the neutral background. So zero occupation, or it's the ground state occupation. Blue corresponds to hole density or lack of charge density, and then yellow is excess electron density. And I should mention that the x-axis is in log scale and is normalized to 1 picosecond. So 0 is 1 picosecond, and -3 is 1 femtosecond. And we can see that after the photoexcitation, the charges cool to the HOMO and LUMO states on a sub-picosecond time scale. And the interesting thing is, if this image had higher resolution, is that there's kind of a smear as the charge cools down to the LUMO state. And so to investigate that feature more, I plot this dotted curve, which is the change in energy over time, to a normalized scale on the next slide. So on the left, the black solid line is the relaxation curve, which includes the spin orbit coupling from the last slide. And the red dotted curve is a fit to a single exponential decay. And then for comparison, for methodology, is a spin restricted calculation. So there's no spin orbit coupling for comparison. And then the interesting thing with the spinor dynamics is that it's fairly quick, up to 100 picoseconds. But then as it gets closer to the band edge, it starts to slow down and extend. I attribute this due to the large subgaps from the spin orbit coupling interactions, which spread out these energy levels in the density of states. And then comparing that to calculation with no spin orbit coupling, you can see that the relaxation is much, much faster, like an order of magnitude, which is due to the absence of the large subgaps in the density of states. And I don't have any figures shown, but if you look at from experimental decay kinetics, I've seen that for small quantum dots, so that this feature quantum dots, and I guess also along the same excited state trajectory, we can compute the photoluminescence along the entire trajectory. Excuse me. So this blue panel is time resolved emission, where the blue is just the neutral dark background. And the colors represent bright states. So up to 100 picoseconds, so this -1, there are low intense or low energy IR emission from intraband relaxation. But then once the charge carriers get to HOMO and LUMO states, it emits very bright photoluminescence from the band gap. And to try to how do I want to say it? So this figure just looks at intensity, but in experiments, another important quantity is how efficient the emission is, which we can compute from computed radiative and non-radiative rates, where the radiative rates come from these Aij Einstein coefficients shown in the top left, and the non-radiative rates come from the Redfield tensors. And we can see that from those rates, we get a fairly efficient PL quantum yield. So we get high intensity and fairly bright emission. I guess the main takeaway from this publication was the slowing down of the carrier cooling near the band gap. Was the most provocative observable from this work. So to state it again, large spin orbit coupling and strong confinement give slowed electron cooling, which can be potentially important for photovoltaics because it would overcome the heat loss assumption from the Shockley-Queisser equations. So study 2 is considering polaronic charge carriers within this atomistic model, specifically looking at changes in carrier cooling rates, and then the possibility of infrared photoluminescence from these polarons. And I guess in terms of summary, one of the main outcomes from that study was that if you include polaronic reorganizations within the nanocrystal, it further helps to slow down hot electron cooling. And I have to check to see if I did this section yet, because I can't find my, because I can't find slides from a previous presentation, which were laid out nicely when I was hoping to just insert. So I might have to remake my slides for this. But I guess just to try going over the methodology aspect for this work, the main methodological problem was to account for the polaronic nuclear distortions in the atomistic models. And for this work, we considered limiting cases. So if you only either added charge by either injecting electrons into the quantum dot somehow, or removing charge by creating holes in the model. And then once you add or remove those charges, allow the model to optimize around the new charge configuration, which should be what you'd expect to have different structural characteristics. And so that was the methodology of how we described polarons for this paper. I'll put my summary slide. Here, so I'll just reiterate the main conclusions from that work is that if you did have a hot polaron, it would help to slow down carrier cooling rates. And then we also try to look for signatures of IR photoluminescence from polarons, but they ended up being very inefficient due to the coupling with the surface chemistry. So there were ionic modes from the surface which were in resonance with the energy gaps where the luminescence would come from. So it led to much faster non-radiative relaxation than radiative. So those were the two main findings from that work. And then the last study that I'll guide you all through is polaron-induced bright trap states. from our models. So the background is that these lead-halide perovskite materials have shown to be fairly tolerant to defects. So even if they don't have perfect surfaces or perfect environments, they are still able to luminesce with not perfect recombination, but like still fairly efficient with like 30 to 40%. Whereas with other semiconductors, defects will radically quench their photoluminescence properties. But here we show that if there's a surface defect site on the surface of the nanocrystal, and you allow polaronic reorganization, you'll have a bright electron trap state for these small quantum dots. And so for this study, I slightly changed models that I considered for this work. So I replaced the oleates with bromine, which helps the simulations be more stable for the workhorse. But I did do calculations for various surface chemistries, but this is the one that I'll show for the slides and that I did for the dynamics. So first I'll consider a fully passivated quantum dot, so there are no surface defect sites on this model, and just consider the density of states in the ground state, so that's the top panel. And then in the lowest excited state, which mimics a photo excitation from this SH band to this SE band. So you can see that there's a small occupation in SE and a hole in SH. And then considering, in this case, just a phase defect, we see that if I manually create a phase defect on the surface and just consider the ground state density of states in this top panel, that the band gap still remains clean. So there's no trap states introduced. But once you allow, but in the lowest excited state, and you allow polaronic reorganization, you see that there's a shallow trap state that forms, which localizes itself to the surface lead, p orbital, and then some of the bromine as well. And the figures on the right show that the SH and SE bands still remain fairly pristine. So there's just a reordering of the energy levels when introducing the polaronic reorganization. So we see that there's a trap state. And then the interesting observation is that from computing the absorption spectra, which is from the transition dipoles shown earlier in the method section, is that these trap states actually introduce some relatively bright optical features. So this magenta and light blue features, where I think magenta considers a phase defect. So it's shown previously, and the light blue is like an edge defect on the surface. And then we still get these bright SH to SE optical transitions from the, I guess you'd say, the pristine band gap. And this is interesting because generally you'd expect that trap states wouldn't contribute bright optical features. And so to further investigate whether there are the possibility of bright surface state photoluminescence, we implement the excited state dynamics. And I will briefly mention that there was a methodology development for the dynamics shown in this paper. Whereas previously I mentioned that we decouple inter and intra-band relaxation, where the solution for this problem is to implement a dampening factor, e to the minus rate constant t, which in this, the rate constant is gamma. And so gamma is the same as RVC and RCV. And then we were able to show that it's possible to transform these full dynamics, shown in the top, and transform them into a damped version of the dynamics by just considering the uncoupled system and applying this exponential decay. So instead of the charge carriers having infinite lifetime, they're now damped to reflect recombination. And you can see that in these two middle green figures. So you can see that the red and blue charge densities, over time, they eventually fade away. And so that's a sign of the dampening of occupations during the trajectory. And overall, there's not a lot interesting with these features. So I should say the top half of the screen is for the pristine surface as a reference. And then the bottom half is the dynamics for the surface trap state with the phase defect. So these are the non-radiative dynamics. Then when we look at the radiative dynamics, we first look on the top half of the screen for the pure surface, or perfect surface, pristine. That there are some hot carrier signals up to, what would this be? 10 to 100 picoseconds. But eventually, once the carrier relaxes the band gap, it gives bright photoluminescence. And note that the intensities are on log scale instead of linear. And from computing the rate constants for radiative and non-radiative, this model showed an overall efficiency of 95% quantum yield. Then when we compare that to the bottom, we say the same features earlier in the dynamics, up to 10 to 100 picoseconds. But then this trap state also shows bright luminescence until it recombines. And it shows the most predominant peak in the integrated luminescence spectra. Then from computing the rate constants, it has a luminescence yield of 75%, which is interesting since it's trap state but has efficient luminescence. So it's a sign of the defect resistance against defects for these perovskite nanomaterials. And show, just to reiterate the findings, is that the polaronic reorganization resulted in shallow electron surface trap states for the models. And then from looking at the radiative and non-radiative dynamics, those trap states showed to be surprisingly bright in nature. And in terms of how it impacts the literature, like there are two main contributions from what I understand. So the first impact is that it could have an impact on the Stokes shift observed in these materials. So there have been publications that it is size dependent and grows, the Stokes shift grows larger with decreasing size of the nanocrystal. So it could be that, like in the non-polaronic state, it absorbs, and then after nuclear reorganization, it lowers the transition energy to give the overall Stokes shift for the small nanomaterials. And then another experimental observation is that with a paper published with Dr. Hobby, we noticed that with decreasing nanocrystal size for these lead-halide perovskites, that they showed a stretched photoluminescence decay. And stretched photoluminescence decay is indicative of having a distribution of recombination sites. And so if these trap states are bright, you could have a mixture of pristine emission along with trap state emission, which would give some rationalization to those experiments. I think that's the last slide, and then acknowledgments to Killen, Kalina, Krajewski, and hobby groups, and also the Lino groups. And then also the collaborator who is always working in the background to help generate data. Yeah, with that, I guess we go to the floor to aggressive questions. I saw there were quite a few going on.
Okay, please join me in thanking Aaron for the effort to deliver this big amount of information at once. So, any emergent questions to be asked verbally? If yes, please go ahead. If no, we'll or after such questions, we'll go over the list of questions typed in the chat line. Okay, it looks like no one is asking questions verbally. So, Levi asking about slide number 3. Wow, that's a lot for me to read. You spent a long time on the picture and size timescales. I know that you are working on charge carriers cooling, but do you need to spend 2-4 minutes on explaining the methodology behind material science?
No, ideally it would be like 30 seconds, but yeah, that's kind of what I hoped for those first 2 slides.
Okay, and I think it makes the presentation oriented to broader audience, especially this time and size scale comparison for multi-scale modeling would be interesting to those who do molecular dynamics as main activity. Levi's question for slide number 4. How does this relate to your work? You are not doing nuclear chemistry. Why spend 2, 3 or more minutes on topics that seem unrelated to your work?
Again, same answer as previous. I guess the main motivation is like we talk to, I don't know, people not even sort of in material science, and it's hard to describe. So it's useful to, I don't know, make a story as how like material science is done in practice. And everybody has an idea of the Manhattan Project.
Maybe it's also related to an attempt to apply for a job at Los Alamos and give them credit.
Yeah, it never hurts.
Okay. Yvonne asking about slide number 7. Pip, the color scheme consistent?
Yeah, if I made the figure, I would, but yeah, it's from, yeah, ideally I would like to make the color scheme consistent, but then I would just have to make the figure myself.
Slide number 10 by Levi. You need to make sure the arrows and animations work if you are going to use animations.
Yes.
Okay, was quite a quick answer. Slide number 10, question from Amir. The order of the animations in the slides show is not sorted.
I think it's the same comment as Levi's.
Yes, yeah, that was the same.
Slide number 13, question by Levi. What is multiple MEG?
I said multiple MEG. That was a mistake, and I put in 2 M's. There should only be 1.
Okay. Questions from me to unknown slide, probably one of the next slide with the electronic structure and DFT. So it's maybe 5 slides later. Or, green with green box in the center. I think it is 19. Yeah. Oh, okay. You already erased. There were 2 indices. Yeah. Okay. Yeah. No questions. Light to matter interaction.